This meeting is being recorded.
In section 11.2, we're going to look at specifically functional group transformations. So this is our topic for 11.2, these functional group transformations. And we looked at some two-step synthesis strategies in recent chapters, in chapters 8 and 9. For example, we looked at how we could perform an elimination reaction to remove HBr. So we remove HBr and we form a pi bond here. And then we saw a subsequent addition reaction where we could move a functional group, in this case the halogen, that bromine, from one carbon to another carbon. So in this case, we would need to obtain our Zaitsev alkene. If you recall, that is the more highly substituted alkene product that's possible with our elimination reaction. And then the second step with the addition reaction, we have Markovnikov addition because the more highly substituted carbon has been installed a bromine. So we'll need to pay attention, even with two-step syntheses, to these types of requirements from step to step. So we saw to move a functional group, we could perform an elimination, paying attention to if we need the Zaitsev versus the Hofmann product, and then we could do an addition to move that halogen, and then we need to focus on if we need Markovnikov addition or an anti-Markovnikov addition. So in this case here, we see we could take different pathways. So if we used a less sterically hindered base, something like sodium methoxide on this top pathway, we would end up with our Zaitsev elimination. So we have our Zaitsev product here, the more highly substituted alkene. If we took this pathway down below with the tert-butoxide, we would see that we get our Hofmann product, the least highly substituted alkene, right? We have two hydrogens here. So we know that it's only di-substituted, or actually it's a mono-substituted, right? The one above is more highly substituted. So let's take a look here. We can reverse that elimination reaction. If we added under radical conditions here, HBr with that organic peroxide, we could install a bromine if we did the reverse path on the least highly substituted carbon. So we can go back and forth between our Zaitsev product and our original starting material, or we could do a Hofmann elimination and then reverse that. So once we're at this point where we have our alkene, whether Zaitsev or Hofmann, then depending on our reagents used in our addition reaction, we would install at the more highly substituted carbon position using just HBr. And that's what we want. That's our target product from the previous slide. Or if we chose the reagents down here, we would have an anti-Markovnikov addition. And this specific double bond, we would install the bromine down here on the least highly substituted carbon. So again, depending on your reagents, depending on your starting materials and your requirements, you choose your conditions accordingly. So say we have an alcohol group here, and we want to relocate that. So in this slide, we're going to focus on the regiochemistry, the region where the elimination is performed, where the double bond's installed. So we have our Zaitsev pathway up here. We have a Hofmann elimination shown down here. And depending on, again, the second step of this two-step synthesis, we would have either the more highly substituted position with an OH installed, or we would have the least highly substituted carbon install that OH group. So let's follow a couple of these pathways. So we have our alcohol to start over here. Let's go up this pathway here. So we have converted our alcohol to a better leaving group by using this tosyl chloride and pyridine. So we've created a tosylate in this first step. And then in the second step, we've used sodium methoxide to perform an elimination to end up with the more highly substituted alkene. If we could also bypass this leaving group, we could use the first the top of the arrow there, two-step mechanism. If we added concentrated sulfuric acid and heat, we could also end up with a Zaitsev elimination. So one step with the concentrated sulfuric and heat, or a two-step process with the tosyl chloride and with pyridine, and then sodium ethoxide. So that would get us either one of those two would get us to the Zaitsev. If we went below, we would have to do something similar um, in our first step. We would use tosyl chloride to create a better leaving group, tosyl chloride and pyridine. And then in a second step, we would use tert butoxide, a sterically hindered base, to give us that Hoffman product. So we could pause here. We could go back to our original alcohol. If we used borane and tetrahydrofuran in this mechanism here, followed by hydrogen peroxide in basic conditions, we would install that OH on the least highly substituted position. So we could reverse our top pathway and go back to our starting material. If we had our Hoffman product, we could reverse that reaction using that mercuric acetate and water, and then sodium borohydride in a two-step mechanism listed right here. So if we wanted to keep going, if we wanted our target molecule to be, say, this top alcohol here, we could use acid catalyzed hydration that we saw with our addition reactions for alkenes, and we would end up with the more highly substituted alcohol. So we can move functional groups such as alcohol groups, hydroxyl groups. We can also relocate halogens. We can also, as we saw previously, move a pi bond. So this is another transformation of our compounds that we can perform. So we have two reactions here. So first reaction, we see an addition to that pi bond, and bromine is installed at the more highly substituted position. We would have a hydrogen down here. Then in our second reaction, we see an elimination. And again, we have to look at the radioselectivity. If we used a less highly steric base, like something like sodium ethoxide, for example, this would produce these Zaitsev products. So we would go back to our original starting material. But so we can't use that here, but we could use something like tert butoxide potassium to generate this Hoffman product here. So again, the reagents chosen depend on the region, the radioselectivity of our double bond. So here's the pathway up top that would be followed if we wanted to do the transformation shown on the last slide effectively. So we see our alkene, we have addition with HBr, so or rather Markovnikov conditions applied here because there's no peroxide. If we went down the pathway here, we would have anti-Markovnikov addition. So since this is a Markovnikov addition, we would choose the top reagent here, just HBr addition. And then, as mentioned previously, we would need a sterically hindered base, such as tert butoxide potassium, to create this Hoffman product. So this was our desired product up top here. But again, we could do an anti-Markovnikov addition, and we could utilize that tert butoxide after that and end up with this product. So again, it depends on your intermediate products and then your choice of reagents as well. So let's look at some more practice here. So say we choose this top pathway for this two-step sequence. We see that radical bromination has been performed, and we've installed this bromine here on that carbon that was highlighted in green. And then we want to perform an elimination to end up with this alkene. So we definitely could do that. We have the skills. In this case, we would end up with a Zaitsev product. So you should know now that we could use something like sodium ethoxide as our base to perform that elimination. What we see down here is how we could interconvert between a triple bond to a double bond. So we can go from alkyne over here by using Lindlar's catalyst. So we add H2, but only one addition to stop at our alkene here. Or we could use a metal catalyzed hydrogenation and go all the way from an alkyne to an alkane. So remember those poisoned catalysts will stop at that alkene step. And then, of course, we could reverse this. We could do radical bromination followed by an elimination if we wanted to go from our alkane back to an alkene. And then we could do bromination in carbon tetrachloride, and then do two eliminations. We have excess sodium amide, so we could then convert our alkene back to an alkyne. So different pathways, different products that result depending on different reagents. So you have to pay close attention to the regiochemistry of your desired product. So we will continue with section 11.3 in the next video.